So far we have taken the time to go over electrochemical cells. I've discussed anode, cathode. We've talked about an ox ate a red cat, which basically means that anode is where oxidation takes place, cathode is where the reduction takes place. Reduction is the gain of electrons, anode is the loss of electrons. So these are a couple things that you perhaps already knew, and we have now started putting things in perspective with respect to the electrochemical cells. And again, electrochemical cells, the best way to look at it is think about batteries. You have chemicals in the battery, and essentially they have the capability to produce electricity and hence be able to convert into usable work, be it a hearing aid, be it your boombox, be it your the battery in your car, whichever kind you're thinking about. Now, anytime you're thinking about electrochemical cells, so far in your head you probably are thinking, okay, I have a beaker which has an electrode, and then another beaker and that has an electrode, and there's supposed to be a wire with maybe like a little bulb, and if the bulb glows I have current and electricity, and I'm supposed to have like a salt bridge. Of course I have an electrolyte here, an electrolyte here, and the electrode and the electrolyte have a common metal ion, and then depending on whichever has a tendency to go through oxidation and reduction, we make a call as to whether which one should be placed where. But the convention is that the anode is on the left side and the cathode is on the right side. Now, we have what are called as cell representation diagrams, which essentially make life easy on us as far as representation of this entire assembly goes. So how do we go about it? Again, we are going to keep the convention the same. That means anode is what is going to occur at the left hand side. Cathode is the reaction that's going to take place on the right hand side. Suppose this was a zinc electrolyte, so zinc 2 plus, and the metal here is zinc, so you have something like ZnSO4 perhaps, or zinc nitrate, because that's going to be soluble completely. And then for copper you have copper nitrate, and you have copper as the metal plate. Suppose this was your electrochemical cell and you had to represent that, and maybe your concentrations are 1.00 molar for zinc nitrate, 1.00 molar for copper nitrate, and that's what you want to go with. What you do is you first write down what's happening at anode. So you start with the electrode. Zinc solid is losing electrons. That means it's becoming Zn2 plus, which is aqueous, and the concentration there is 1 molar. Notice this one single line, which essentially signifies the interface of the electrode. Interface of electrode. We then put a double line, and that signifies the salt bridge. Salt bridge. And then next we will write down what's going on at the cathode end. At the cathode end, copper 2 plus ions are going to accept electrons and deposit as copper metal. That means copper 2 plus is going to be written as aqueous and then 1 molar. And that's going to take up electrons and deposit copper solid as your final product. This method of representation is what is referred to as the cell representation diagram. So it's much easier, much more simpler as to how we go about it. I'm going to still give you a little bit more practice so that you're able to write that, but it will show up in dry labs and some take-home quizzes or an exam, so you should know how to go about it. Again, we still follow the convention, anode on left, cathode on right, but you have to think about what's happening as a process. Since anode covers oxidation, this must show that zinc has lost electrons the right side must show that the copper 2 plus has gained electrons. You can't write Zn2 plus line Zn. You can't do that because that would mean that the zinc is undergoing reduction, and that's not allowed in this particular situation. Sometimes the cell representation diagram is also referred to as a line notation, because these vertical lines are for the salt bridge and the interfaces for the two electrodes. So sometimes it's also referred to as the line notation. But in this representation, hopefully you have appreciated that we have written both the oxidation half reactions and the reduction half reaction on the left and right side respectively. The double vertical line, which is the salt bridge that separates the two half reactions, and the substances that are present should be shown in different phases, and the concentration of the electrolyte that you have kept. So let's take a look at another redox reaction, and what I'll do is I'll write down, let's take it stepwise. I'll write down what the oxidation is, what the reduction is, and perhaps you can then figure out what the cell representation diagram should be. Okay, so the information that is given to us is that we have an oxidation half cycle where electrons are lost, and then we have the reduction half cycle where electrons are gained. Right over here, electrons are gained, and this is all occurring in acidic media, and Mn2 plus and H2 are generated. So the fact that you are already provided with the information as to what's oxidation, what's reduction, that makes this cell pretty straightforward. Let's write down the overall reaction first. The balanced equation should be, since you have 5 electrons for the reduction, only 2 for the oxidation, you must multiply the oxidation half reaction by 5. You must multiply reduction half reaction by 2 so that it reflects the same number of electrons, and you can say that is going to be 5 Fe plus, so I'm going to essentially do 2 steps together. I'm going to multiply and I'm going to add both the equations to get the overall redox. So 2MnO4 plus 10 electrons plus 16 protons gives you 5 Fe2 plus 10 electrons plus 2 Mn2 plus 8 water. The 10 electrons are going to cancel off. Went too quickly there. The 10 electrons are going to cancel off, and what remains is your overall redox reaction, which is 5 Fe solid plus 2 permanganate aqueous plus 16 protons aqueous gives you 5 Fe2 plus aqueous, 2 Mn2 plus aqueous, and of course H2O is going to be a liquid. Now, we have our half reactions, we have our complete redox reaction. If we were to write down the principal species which are all going to be involved in the cell representation diagram, the way we would write that is going to be Fe, which is in the solid phase, separated from Fe2 plus, which is in the aqueous phase. Now realize in this case they haven't provided any information on the concentration, so that's okay, we won't worry about it. And then we have the salt bridge, and of course we have MnO4, which is present with the proton. So both of those are your reagents. Both of these are aqueous as well. Anytime you have a charge, that automatically is aqueous. We learned that in chapter 15. And what else? We have that as a, let's see, we have that as a reaction that gives me manganese 2 plus, and this reaction is done essentially in presence of an inert platinum electrode. So the electron transfer requires an electrode on which the reaction should take place, and we usually utilize platinum electrodes. So that kind of information will be provided to you, and using this information you can say that Mn2 plus and all of that is occurring at the platinum electrode, which is your solid. So the platinum being on the far right tells you that the inert platinum electrode acts as the cathode for the reaction to take place. But even so, what's happening is that the permanganate is reacting under acidic conditions to give Mn2 plus. All of those are aqueous phase. So this is one of those situations where the reactants and the products, or maybe both of the half reactions, they are all occurring in the same phase. And in such cases, then you have to use an inert electrode such as platinum or graphite, as anode or cathode, or perhaps even both. So that was just an example that covered two things here. So hopefully you can recall the steps. The steps are, when you know the two half reactions, make sure, verify that it is balanced. So you must start with a balanced redox reaction to get an idea for the number of moles of each case. And then put your anode on the left hand side, put your cathode on the right hand side, the side that contains all the reactants as well as the product, and in this case that happened to be the cathode reaction. And so when that kind of a situation arises, such as in this case everything here was aqueous, essentially then you require the presence of an inert electrode, and in this case we employed platinum, which is the inert electrode. Okay, that brings me to the standard electrode potentials, which usually are given by Inert Cell for any electrochemical cell. And it really depends on the specific half reactions that are occurring in the half cell. But the standard electrode potentials, those are measures of the potential energy difference. So this is a measure of, let's write that, it's a measure of the energy potential energy difference potential energy difference that is between the two electrodes, between the two electrodes. So you can say that it essentially gives you an idea about the tendency to go through oxidation versus tendency to go through reduction. You can think of it that way as well. So one way to think about the electrode in each half cell as having its own individual potential, which will also be referred to as standard electrode potential. And the overall standard potential for the cell is then going to be the difference between the two standard electrode potentials. So what we are saying here is that we have an anode and we have a cathode. This is anode, this is cathode. Now we are saying anode will have a tendency to lose electrons. And how is that tendency measured? That tendency is measured in terms of the E naught electrode potential for the anode. Likewise, the cathode will have a tendency to gain electrons, and that will have some E naught, some electromotive force, some standard electrode potential associated with it. And the difference between the two, the difference between the two standard electrode potentials is going to give you the E naught cell, which will give you a fairly good view, a fairly good idea about whether the cell that you have in question, whether that's a spontaneous cell, whether the electrons are going to flow, the bulb is going to glow or not. So we're going to get a fairly good value that we should be able to start predicting that as well. I mean, one way to look at it would be if you consider, let's say, maybe two tanks. Okay, there are two water tanks and they have different levels of water in them. So one is at a high level, another is at low level, and you somehow are able to connect the two. You can perhaps see that almost spontaneously. I mean, you don't have to do much, but the water in each tank has a level and it corresponds to a certain potential energy. But when you connect the two tanks, water flows from the tank which is at a higher level to the tank which is at a lower level. And in the same manner, you can even envision that each half cell in a electrochemical cell has its own charge and corresponding electrode potential, and hence when the cells are connected, electrons flow from the electrode which has more negative charge to the electrode which has more positive charge. So that's one way to look at it, and that is the reason why earlier when I gave you that it was the anode which essentially has the is the negative electrode. Electrons are going to flow from anode to cathode. That will be the direction of flow at all times, anode to cathode. Now, one thing hopefully that you do remember is that when you have an electrochemical cell and you basically connect the, two through a wire, and you can put like a bulb or you can put a voltmeter, you would be able to measure the overall potential for the whole cell. However, you would not be able to measure the potentials for each of the two electrodes. And if you need that information, then you will have to, take the time to essentially get a reference, like an arbitrary a potential where the anode can be compared to a standard hydrogen electrode, which has been arbitrarily picked up to have a value of 0. And then you can do the same thing for cathode as well, and you can come up with the value for each of these anodes and cathodes. And so now when you hook up the two together, essentially what you're saying is that those are the values that you calculated with reference to that standard hydrogen electrode. So let me go into detail as to what I mean by this. Let me give you an example about it. The point of reference is what is called as the SHE, or the standard hydrogen electrode. Okay, and the half cell electrode that is normally chosen to have a potential of 0 is the SHE, or the standard hydrogen electrode. And this half cell basically consists of an inert platinum. So there's like this platinum plate, and there's a wire that holds that plate, and this is immersed in 1 molar HCl. Okay, and so that's your HCl, that's your beaker, and hydrogen gas, H2. So what happens is that we bubble hydrogen gas at 1 atm. We bubble that through the solution. So this is just a rough schematic, and we have that in the PowerPoint as well. So when the SHE acts as the cathode, so when it acts as cathode, okay, cathode means that it's supposed to then gain electrons. That means the H plus in the acid, the H plus is going to accept electrons, 2 electrons, and it's going to generate H2 gas. And we are saying that the E naught for this is 0.00 volts. Now, if we connect the hydrogen, the SHE, to an electrode of another cell, okay, another cell that we are interested in determining the potential difference of. So we want to determine the potential difference of some electrode, and so I'm going to hook up SHE with that other electrode that we have. So you could consider, perhaps zinc, for instance. So zinc is going to go to zinc 2 plus, and I know that that will happen because if you put these in the reactivity series, zinc is higher than hydrogen. That means zinc has a greater tendency to go through oxidation or lose electrons. Hydrogen, on the other hand, is going to gain electrons, so it's going to be reduced to H2 under standard conditions. So what that means is that your concentrations are all 1 molar, pressures are all 1 atm, and temperature is 25 degrees Celsius. So what's going to happen? Essentially, your electrons are going to travel from the anode to the cathode. So you can define the E naught cell as the difference in the voltage between the cathode, which is the final state, and the anode. And so one can say very conveniently that if zinc was the anode and hydrogen was the cathode, and here's your electrode, here's the wire, and then of course you have the salt bridge also. What we are saying is that zinc gave you Zn2 plus, hydrogen accepted those electrons, gave you H2 gas. If you wanted to determine the E naught cell, essentially you would say that the difference in the voltage between the cathode, E naught cathode, minus E naught anode is what is going to give you your overall E naught cell. So it's always is final minus initial. Okay. Now, for this particular case, the measured value of 0.76. That means once these were hooked up, essentially the measurement of the cell came out to be 0.76 volts. And we are saying that that came from E naught cathode minus E naught anode. So could I say, just basic math, that E naught anode is going to be negative 0.76 volts? And the reason why I say that is because the E naught cathode, this number here, is 0. So when you plug in the numbers, it's going to give you a more negative voltage. That means a higher potential energy than the cathode itself. So if you had to write down the cell representation for this particular cell, you would say that this is a combination of zinc going to Zn2 plus and hydrogen is becoming hydrogen gas, and that's happening at the platinum electrode. And of course, there's a salt bridge that's going to separate the two out, but those are the two basic reactions that are occurring in this particular cell. So if the concentration is given, you would, provide that. If not, that's okay. But left side is going to continue to have the anode. Right side is going to have the cathode, and the voltage associated with zinc is negative 0.76 volts, and we use the word standard electrode potential, and this is how it's measured. Again, the value for hydrogen that has been randomly chosen to be 0, and any measurements that we make for any electrode for that matter are going to be with respect to this hydrogen. So one can say, just the same way as we discussed, I gave you the analogy with like two beakers connected with water, and then high potential energy moving to low potential energy, or high level of water going to low level of water. It's the exact same story if you set up this particular cell. Electrons are going to spontaneously flow from anode to cathode, that means from zinc to hydrogen. And the reason for that is because anode in this case, it is at a more negative charge, it is at a higher potential energy than the cathode, so it has a tendency to give up that electron, and zinc would rather spend its time as Zn2 plus the two electrons, and those two electrons then flow over on the other side and combine with hydrogen to give hydrogen gas. So again, we can say this as if potential energy diagram, that the anode in this case, the electrons, two electrons, they can be given spontaneously to the cathode. This is anode, this is cathode. And cathode is where the 2H plus 2 electrons will give you hydrogen gas. Anode is where Zn will give you Zn2 plus 2 electrons. And this is as the negative EMF. And of course, your hydrogen is at 0. All right. So far what I have told you is that for every electrode we can measure standard electrode potentials, and these values are not just measured specifically, but rather with reference to a hydrogen electrode. So that's my reference electrode, or also called as the standard hydrogen electrode, and the number for that was randomly picked to be 0. And so now the value that you get with reference to that, that's how we figure out the electrode potential. That means what one would do is one would hook up an unknown electrode, any given unknown electrode, and you can choose that. If you don't know anything about it, you can just choose that to make an anode and the other one as a cathode. If the reaction is spontaneous and electrons flow, then the bulb will glow. On the other hand, if the reaction is non-spontaneous, the bulb is not going to glow. So you will have to reverse the polarity to make it work, and so what we also learned in this case is essentially that the negative potential, what does that indicate? The negative potential indicates that an electron, for that electrode, it has a greater potential energy, and greater is the potential energy, more negative that electrode potential will be, because essentially that negative charge that is being accumulated, it's going to repel that electron. So anytime you see a more, let's write this down, more negative electrode potential, more negative electrode potential, that means that particular electrode, it has tendency to undergo oxidation, tendency to undergo oxidation. And that also means that since the negative charge repels the electron, the potential energy of the electron at that electrode is going to be higher. Now the question is, what would happen if we connect an electrode with an electron that has a more positive potential? So more positive than the standard hydrogen electrode, yes. So then that would mean that that electrode has a more positive voltage. That means it has a lower potential energy. That means it's going to attract the electrons towards itself. So again, you can determine whether a certain electrode is going to undergo. Once you have the values, you can determine whether a certain electrode has the potential to go through oxidation or reduction on the basis of their electrode potential values. Electrode potential values. More negative is the value, since oxidation occurs at anode, that is your negative electrode. It means that you're going to have an accumulation of electrons there. More positive is the value. That means it's at the cathode. That is where gaining of electron is occurring. Electrons are not produced there. So that's how you can determine what is anode, what is cathode. And we are going to do a little bit practice in the next video for that as well. But for the time being, suppose we connect a standard hydrogen electrode to a copper electrode, which is immersed in a 1 molar copper nitrate solution. And when you measure the cell potential for the cell, so I have, let's say, negative 0.34 volts is the measured cell potential for the cell. Okay, now you can, like I said, if it's an unknown, you know nothing about it, just randomly pick and make that the anode. So you have copper 2 plus, which will happen at anode, and that is going to be an hydrogen plus to H2, that will be at your cathode. So I'm going to do exactly what we did a couple minutes ago, where Inert cell is equal to E naught cathode minus E naught anode. And so when you measure out, since E naught cathode is 0 and E naught cell came out to be negative 0.34, you can perhaps envision that E naught anode comes out to be plus 0.34 volts. Well, what does this mean? This means that this anode is at a more positive, it's anode and it's at a more positive voltage. That means it's at a lower energy as compared to the cathode. And so the electrons are not going to spontaneously, they're not going to go spontaneously from the anode to the cathode. That's not going to happen. And so if you will, the potential energy, if you were to draw that, you have the two electrons, they are at a lower energy, and we want it to go to a higher energy state. Well, how would that happen? That's not going to happen. So the copper half cell is kind of like a water tank in which you have a lower water level, and the electrons do not want to spontaneously flow from the copper electrode to the hydrogen electrode. So then what do? Well, there is not much that you can do. This just means that since the value that you have is a positive value, that would mean that copper, with reference to hydrogen, is going to be lower in the reactivity series, whereas zinc, that we got essentially a negative number for, it's going to be higher in the reactivity series. That means tendency for zinc to undergo oxidation reaction is going to be easy as compared to hydrogen, and hydrogen is going to be better as compared to copper. So if you were to, essentially put these reactions together, you would say that copper plus 2 electrons giving you copper solid, E naught is 0.34 volts. And I'm writing these as reduction half reactions because by convention, and this is a more modern convention, these are reduction potential values, or these standard electrode potentials are written for reduction half reactions. And there was a time, some 30, 40 years ago, when people used to talk about oxidation potential and reduction potential, but a lot of times they would not be able to predict whether the cell would work or not, and their calculations started to get a little haywire. So they decided to just stick to a reduction potential value, and that's why we have the rules that we have are only for the reduction potential values. So right now I'm saying that between zinc and between copper, those are the two that I have seen, we can see that the copper electrode is positive relative to SHE, and the zinc is negative relative to SHE. What does that mean? That means that copper, because it's positive, it will tend to draw away electrons from the SHE, whereas zinc, which is negative, is going to essentially repel electrons towards the standard hydrogen electrode. And so hopefully you have been able to see certain things. Just to summarize, before we move forward, the SHE has been placed randomly. It's a random number that we came up with, 1, and so it was a relative scale. Everything else was with respect to the standard electrode. The electrode in any half cell with a greater tendency to undergo reduction is going to be positively charged with reference to the SHE, and hence it would also end up having the positive E naught. So positive E naught means that will undergo reduction or gain of electrons, or electrons are sucked towards it. Electrons move towards it. And the negative E naught, that means that it will undergo oxidation, because that's the accumulation of electrons. That means the negatively charged electrons are moving away from this electrode, and that happens when oxidation takes place. So this must be your anode. So you can say whenever you're given two electrode potentials and you have to predict which one is the anode, which one is the cathode, whichever is more negative, that's going to be your anode. Whichever is more positive is going to be your cathode. And of course, you know the rules, how to go about the cell representation, so we can put things in perspective now. If we have to determine the E naught cell, that always is going to be cathode minus anode, E naught cathode minus E naught anode, and the E naught cell that you obtain, it will end up being overall a positive value for a spontaneous reaction, a negative value for a non-spontaneous reaction. And we'll take a look at that also in a subsequent video.